Hello, everyone. My name's Nick. I'm a developer at IBM, and today I'm going to be talking about what object detection is. To start, here's a photo of a cat. If I were to show you this photo of a cat, you would probably say, this is a cat, because it's a cat. And this is what we call classification. It's showing a computer vision model a photo and getting a label back. But what if we were to get a picture that looked something like this? We can't say there's a cat, and we can't just say there's a dog, because there's a cat and a dog. And this is where object detection is really helpful. With object detection, we're able to specifically point out in a photo where the cat and where the dog is and what labels they are. This is really helpful if we wanted to count how many animals were in a photo and know exactly where they are. So how do we do this in real time? A lot of companies like IBM, Google, Microsoft have object detection APIs where you can just upload a photo and it'll give us back where objects in the photo are and what they are. And I'm going to show like a little demo of this. So I have, oops. Okay. This is an example of object detection with an API. I'm not actually using an API. It's simulated from my office Wi-Fi, which has very good Wi-Fi. Because if we were doing it here, it would probably take way, way, way too long. So if I hold up a thumbs up, it should be able to detect. But as you can see, it's pretty slow. Not very user-friendly, kind of useless almost. And it's like a simulated latency of about 1 second per frame. And that's really good. So if we were to use like the conference Wi-Fi, it might be like 5 seconds, which would just be pure garbage. So what if we just move the model to the front end and just use JavaScript to code out our model? So here's an example of that. Cool. All right. So here's the same model again, but this time it's using JavaScript. All right. And it's almost slower. And here, I'm going to, oh man, really slow. Inspect the page, and I'm logging out how fast it's taking. And it's kind of really tiny, but there we go. Woo. Okay, so it's taking about 2, 3, 5 seconds per frame. So this is worse than the API that I was using. And the reason, I should stop that before my computer burns up. Back to the... So deep learning is a bunch of matrix math. So in JavaScript, we don't really have threads. So we have to go through each element in the matrix one by one by one by one. And this takes kind of a long time. For most cases, not too long, but when we're dealing with images and we're doing lots of layers, that layer by layer, or cell by cell, takes a lot of time. It adds up. And that's where WebGL comes in handy. With WebGL, we can give it a specified output, and it can calculate all of them pretty much at the same time. We can do multiple things at the same time. So let's take a look at this matrix right here, A and B, and let's say we wanted to add them together. Using regular JavaScript, we would have to loop through A and B and add 5 to 3, 7 to 1, 4 to 1, and so on through the whole matrix. But with WebGL, we can write a shader which essentially can pick any random cell in the output and calculate what its value should be. So if this bottom right-hand corner cell, it gets the coordinate from A, which is 4, from B, which is 3, and adds them together, which gives us 7. When we do it this way, and each cell kind of has this function that can be applied to it, we can calculate all 9 at the same time. And that's where TensorFlow.js comes in handy. It has a bunch of this matrix math already pre-built into WebGL shaders. So we can write our own sort of functions, or we can just download a model we trained with TensorFlow and convert it to TensorFlow.js, use that model, and it'll be much, much faster. And here's an example of that. And let's hope this time it goes fast. So now it should be using the GPU in WebGL. Cool. Oh boy. So as you can see, it's much faster. Still a little confusing because there's like 3 of me in this thing. And then if we look here, it's only taking tens of milliseconds, which is much, 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 much faster than using just regular JavaScript, and a big step up from using the API. So the next question is, how do we train an object detection model? So basically we have our AI, and we have a bunch of images, and we have to go through all these images and label every single cat, every single dog, and tell it that it's a cat and dog, and feed it to this AI and start training a model. And most state-of-the-art models are trained on millions of images. So you might be thinking, what? That is crazy. I don't want to label millions of images. And you might also be thinking, I can look at an object once or twice, and then I can kind of identify it. So like if I showed you this water bottle, you could tell me that this is probably like a similar, same company water bottle if you've never seen this brand before. So before we answer that question, I'm going to talk, what do computers see? This is what computers see. Probably looks like nothing. Even with this huge screen, you probably can't even read all the numbers. But it's just a bunch of hex codes representing each pixel and their color value. So let's play a little game. Here's a nice photo of a cat. It's the same cat we saw earlier. Remember that this is a cat. Here's a dog, all right? We know what dogs look like. That's definitely a dog. All right. So, is this a cat or a dog? I want to see a raise of hands here. Come on. Who thinks it's a cat? A lot of you think it's a cat. Who thinks it's a dog? Okay, a few of you. It is a cat. I'm very impressed. Great job, everybody. So, why can humans learn so quickly? I don't know about you, but I've been learning for over 20 years. You guys might have been learning longer. Who knows? What have we been learning all this time? One thing is shapes. So if we look at this nice photo of a cat, we can still tell it's a cat, even though it's not an actual cat. It's just a shape of a cat. And if we look at this photo of a dog, we can probably tell it's a dog, even though it's just a shape of a dog. And the reason for that is that when we look at an object for the first time, it it's not this unstructured mess of light intensities. It gets kind of put together in shapes and lines and curves and edges, and we kind of have a hierarchical understanding of the image. We can break it down. And when we train AI on millions of images, it starts to learn these same concepts that we learn. So it can kind of tell edges and shapes and stuff like that. And we can use this. So when big companies train a model for the first time on millions and millions of images, it starts learning this. And we can take this knowledge that it already has learned and kind of build on top of that. So we might have a model that can detect cats, dogs, people, cars, trains, very general objects. But let's say we want to do thumbs up, thumbs down. We don't have to train it on millions of images of thumbs up, thumbs down. We can take the model that was trained on the other things and teach it what thumbs up and thumbs down is. So it already has like this basic information of the edges and shapes, so it doesn't have to relearn that. So we can show it much, much less photos. Yeah, so we can recycle it, don't have to start from scratch. What else have we learned? We're going to play another game. How exciting. All right, so I'm going to show you a bunch more photos. They're very abstract, and they're labeled A or B. So this is A. This is B. Really soak it in. This is A. B. Neither A or B. And this is also neither A or B. So what is this mystery image down here? Any, let's raise your hand if you think it's A. Okay. Who thinks it's B? All right, I think we're pretty evenly split. So this was A. Why is it A? Because I said so. So the reason why I thought it was A was because I only really cared about this center object. In A, the center circle is red, and in B, it's yellow. And neither A or B, we have a pink circle and a red square. And so I showed you a few photos, and it's not this crazy blur gray mess. It's shapes, so we should be able to tell. And why can't we tell? As you see, only half of you got it right, is because we have context. So if I showed you this same example, but less abstract, if I asked you what this mystery photo was, I hope most of you would say A, right? It's an apple. And so yeah, context. So when we see this photo, we can kind of throw out the background and the hand, and we're just kind of left with this apple. So when somebody's like, what is this? We kind of know. We don't have to start from scratch and like, are they talking about that door over there? No, it's probably what they're holding. And these machine learning models don't really have this kind of context. So even though we can teach it these shapes and lines and stuff, it still needs a decent amount of photos to learn if something is an apple. So like 50 photos or something instead of just one photo. And then so here we have another example. On the left we have palm trees, and on the right we have oak trees. Or I guess for you guys, left oak, right palm. And if I showed you this next photo, it's a palm tree, but it kind of looks like an oak tree almost, maybe because it's so dark. And that's because when we show a computer vision model this, it might accidentally learn that we're just trying to teach it dark versus light. It doesn't really know we're trying to teach it that it's an oak tree. This is kind of referring to an urban legend kind of thing where the US military was trying to build an artificial intelligence model that could detect US tanks versus Russian tanks. And we took a bunch of photos of our tanks and we took a bunch of photos of Russian tanks and we trained the model. It was a success, but when we went to go try it, it didn't work at all. It was horrible. And the reason for that is because it actually did learn, but it just learned to tell if it was daytime or nighttime. Because I guess for some reason we could only take photos of our tanks in the daytime and the Russian tanks at nighttime. So it's important to kind of think about this sort of miscommunication. We can't really tell the AI exactly what to learn. We have to kind of coax it into learning what we want it to learn without specifically saying, pay attention to the tree, because it doesn't know what a tree is. It doesn't know what part you're trying to teach it. So to kind of combat this, it's good practice to take lots of photos with different backgrounds, different brightness levels, so we're not kind of teaching it these other things on accident. So today we're going to talk a little bit about labeling, training, and then using. To label it, I like to use a tool called Cloud Annotations. I like to use it because I built it, so it's perfect for my needs. And to train, I'm going to use Watson machine learning because I work at IBM. And what Watson machine learning is GPUs on the cloud, so we can upload some training code and it'll train a model for us on GPUs, so we can train it a lot faster than just training it on a laptop. And then to use it, we can either use CoreML, TF-Lite, or TensorFlow.js. And CoreML is great for iOS apps or tvOS or your iPad, your Mac, anything Apple related. TF-Lite is great for just anything in general, almost. So Raspberry Pis, Android phones, iPhones, pretty much anything that can run Python or C or anything like that, or Java. And then TensorFlow.js is good for what we saw just earlier in the browser. And yeah, so now I'm going to go through how to actually use cloud annotations and train the model and then actually use it. So here's the GitHub for the project. It's probably really tiny, but it's github.com/cloud-annotations-training. And it has a nice workshop, so if you're interested, you can go through all the steps on your own on how to do all this. And the tool itself is cloud.annotations.ai. And then you can log in with your IBM Cloud account, and it's attached. Oh boy. Gotta log in. And so it's attached to an object storage bucket. So you can, when you upload all your photos, they're saved, and along with all your annotations, and you can invite users to collaborate and work on a project together, because even though we don't have to label millions of photos, thousands of photos can end up being a lot too. And I should plug my laptop in. Thank you. Okay, so when we get to cloud annotations, I have lots and lots of buckets because I've been doing lots of these. All right, so we need to name a bucket, so I'm just going to call it thumbs up or down. And then we can choose either classification or localization. And localization is what gives us the ability to actually label our photos with all the rectangles. And then we can upload videos or images. So I'm going to use Photo Booth. Oh boy, that's loud. Oh, that's not what I wanted. There we go. Okay. All right, so now it's recording me doing some thumbs up, thumbs down. And then I'm just going to drag that in. Now it's recording me. Oh gosh, please stop. Thumbs up, thumbs down. Oh, it's always horrible hearing yourself talk. All right, so it's going to upload all these photos or video and split it up into frames. And then I'm going to create a label, thumbs up and thumbs down. And then we can just go through and start labeling. Super fun. Those of you who came to my workshop the other day know how fun this is. Cool. Let me find a nice thumbs down. There we go. All right, I'm not going to label all of them, but I recommend if you're trying to build a model, something that's semi-useful, around 50 images per label. So 50 thumbs up, 50 thumbs down will give you a pretty solid model. The model that I showed earlier, that was 50 of each. And this wouldn't make a very good model because it's all just me in this room in this lighting. So again, it's good to get video clips of you doing it in a bunch of different places. And then once you label all of your images, you can export your model as like the YOLO format, CreateML, or Pascal VOC. And those are some pretty widely supported annotation formats, so you could use it to train a model on your own. But we're going to use Watson Machine Learning, which we have a nice CLI for. I should make this bigger. It's called CACLI, which stands for Cloud Annotation CLI. And you can get it by npm installing cloud annotations. And then that might take a little bit of time, depending on our Wi-Fi. And so this cloud annotation CLI, wow, so fast. You can run CACLI login to log in. Please don't steal my credentials. So it's asking for Watson Machine Learning credentials, which are already provisioned in IBM Cloud. And then the Cloud Object Storage credentials, which are the credentials attached to whatever bucket. So this thumbs up, thumbs down bucket. Actually, I think these are different credentials, so we won't see this bucket. And then we can run CACLI train. Wait. I already have a config file. All right, now CACLI train. It's going to ask me to log in again. So here's my credentials again. More opportunities to get unlimited access. All right, so I have two different buckets here. I'll use the thumbs one. And I'm not going to store it in a separate output bucket. You can do this if you want. Sometimes it's helpful to have all your images in one bucket and then all of your models in another bucket, because I start getting like millions of models and then I can just delete that bucket instead of going through and finding them all. And then so it'll validate my config file and start a training run, and eventually it should give me a nice model ID. And with that model, there we go. So it submitted my training run. It gives me this model ID. So at this point, I can just close out. And then with that model ID, I can either monitor the progress or download the model once it's done. I'm going to run CACLI list to see if I have another model that's finished training, because even with the GPUs, it can still take like a half hour to finish training. All right, so I'm going to CACLI download this water bottle model. And I'm going to just pass tf.js. If you just run it as is, it'll download all of the different model formats, which would probably take some time on the conference Wi-Fi. But this should just download the TensorFlow.js model, which has the model for thumbs up, thumbs down. But where'd that page go? Cool, yeah, so here's the GitHub. If we go to the main org, there's this object detection React repo. Cool, downloaded. So somewhere in this folder, there should be a model web folder. Here we go. So here's our model. And then back to the React application. So you can clone this or download it. And inside, there is a public folder. And this is where we're going to put our model we just downloaded. So you can just drag that in. Now we're good to go. We're ready to use the app. And this model is probably not a good model because I think this is the model I trained the other day with just like 2 or 3 of my thumbs up. Where did I save this? Downloads. Cool. And then just yarn install, or actually npm install. And then that will install all of the requirements for this React app. And one of those is this object detection JS module, where this is where all the TensorFlow JS is actually happening. This is just a wrapper, so you can just call model load to load the model web, and then model detect to get the actual predictions. And this is what the predictions will look like. So it's an array of the bounding box coordinates with the class and then the confidence of that class. And you can pass anything to this detect function. So it can be an image tag, a video tag, or a canvas tag. And whenever you call the detect function on that tag, it'll take a snippet of what it looks like at that point in time. So if we pass the video tag and then we just loop for every frame and keep running detect, it'll detect for each one of those frames. Cool, so that. And then you can just run npm start once all that installs, and we'll be greeted with our web app. And it probably won't detect anything or it'll probably detect everything. You can do this. Oh gosh. But yeah, so it would be what we saw earlier, but with my bad model. And that is all I have. Thank you. Any questions? Yes.
How big are those models? Because if you serve those files, a user is going to take a while, right, to download that.
So the question was, how big are the model files? And the TensorFlow JS model file is about 20 megabytes. So it's about the size of an image, so not too bad. Cool. Thank you. Oh, yes?
You have to change your password because everything is...
Yes, I will need to change my password. I might forget though.